Hey boys, 4.7 absolute value inequalities, page 145. This is another one of those lessons where it's pretty straightforward. It's just expanding our rules to inequalities as opposed to just equal signs. So let's get to it. So recall we have absolute value signs. In all absolute value is, as it says, whatever's on the inside, make it positive. So -6 becomes 6. Positive 6 becomes 6 as well. Another way of thinking about that is how far is our number in the middle away from 0 on a number line. So take, for example, down here, we've got -6, we've got positive 6. So the absolute value of -6 means it's 1, 2, 3, 4, 5, 6 spaces away, and the same thing for the positive 6. So before, if we wanted to figure out what our number on the inside was, let's say x plus 1, or the absolute value of x plus 1 is equal to, let me make this a 2, that way you don't confuse my ones. So these are absolute values bars. So x plus 2, the absolute value of x plus 2 is equal to 7. So remember, we've got ourselves parallel lines, so our memory trick is parallel universes. So one where we make two equations, one where x plus 2 is equal to 7, and one where x plus 2 is equal to -7, and then we solve for x. On each, x equals 5, x equals -9. And what that means is these are the values of x that make our statement up here true, because 5 plus 2 is 7. The absolute value of positive 7 is 7. -9 plus 2 is -7. Absolute value of -7 equals 7. Now, let's take a look at what our rule looks like with inequalities. So let's do x plus 2 is less than 7. All right, so just like before, we're going to do parallel universes. So, well, let me go ahead and do the other example first. So we can have x plus 2 is less than 7 or less than or equal to 7. Doesn't really make a difference right now. And we also have x plus 2 is greater than 7. So let's take a look at our take a look at our parallel universes. So let's start with this one over here. So we want to do one parallel universe where x plus 2 is greater than 7, and we want to do one parallel universe where it's negative. So x plus 2 and -7, but remember our rule where whenever we multiply or divide by a negative number, our sign flips. So the same thing here. So instead of pointing to the left, our sign is now pointing to the right. And that's just because we changed it from a positive to a negative. So let's go ahead and just solve for x. Solve means get x by itself, -2 minus 2. X greater than 5, -2 minus 2. X is less than -9. And actually, it would make more sense if we did it this way. X is less than -9. X is greater than 5, or x is greater than 5 might make more sense in this context. And so let's take a look at what graphing that looks like. We've got, let's say -9 is over here. We got x less than -9. Actually, it's an open circle because it's less than. Oops. And then we got x greater than 5. So if you pick any x from these lines going forward, you'll make the statement true. Let's take a look at what happens if we pick something not included on the line. If we choose 1, for example, 1 plus 2 is 3. 3 is not greater than 7. And let's take another example. Let's take -5. -5 plus 2 is -3. -3. Absolute value of -3 is 3. 3 is not greater than 7. So that's one case. And it's pretty much the same thing over here with this case, but let's take a look at what's different. So same thing, parallel universes, x plus 2 is less than 7, and then x plus 2 is and negative 7, but we flip the sign, solve for x. X is less than 5. X is greater than negative 9. So you may think it looks the exact same, but let's keep drawing it in the wrong order. So we got x is greater than negative 9, x is less than 5, and let's go ahead and just move it around a little bit. Oh, is that the right button? Yeah. Negative 9 is less than x, x is greater than 5, and if we look at these are nice because we can actually turn these into one phrase. X is greater, negative 9 is less than x is less than 5. So it doesn't make a difference whether you write it like this or like this. It's just more concise if we write it like that. And let's take a look at what graphing that looks like. So we said x is greater than negative 9. So x greater than negative 9, but x is also less than 5. And if we look, we've got a nice line segment as opposed to before when they shot out in each direction. So let's take a look at another example here from the book. All right, the absolute value of 2 minus 1 is less than or equal to 5, so parallel universes, 2x minus 1 less than or equal to 5, and also 2x minus 1 is greater than or equal to negative 5, because the signs flip when we multiply or divide by a negative. That's what we did when we went from 5 to negative 5. So get x, solve for x, plus 1, plus 1, plus 1, plus 1, 2x less than or equal to 6, 2x greater than or equal to negative 4, x less than or equal to 3, x greater than or equal to negative 4. And if we take a look at these, we can also see that we can rewrite these as one phrase where x is greater than or equal to negative 4 is less than or equal to 3. And if we wanted to graph that, it would go from here, negative less than or equal to, greater than or equal to, so they're filled in dots, and it goes from here to here. Perfect. So this is a good problem right here. The absolute value of 2 minus 1 times 3 plus 1 is greater than or equal to 10. So you might want to use parallel universes, but remember we can't do that step until our absolute value is the only thing on the left side. So we kind of got to treat it like a variable right now before we can use it. So let's just pretend this is all one big chunk that we need to get by itself. So it's being multiplied by 3 and added by 1. So do the opposite of that. 3 times the absolute value of 2x minus 1 is greater than or equal to 9, and then divide both sides by 3, and we've got the absolute value of 2x minus 1 is greater than or equal to 3, and now since our absolute value is by itself, now we can use our parallel universes. 2x minus 1 greater than or equal to 3, 2x minus 1 less than or equal to negative 3. And then we solve, and that gives us 2x greater than or equal to 4, 2x less than or equal to negative 2, divide by 2, x greater than or equal to 2, x less than or equal to negative 1. And if we think about in this case, it's greater than the positives and less than the negatives, so we're actually going to split it up this time. X greater than or equal to 2, so greater than or equal to, so filled in, less than or equal to, so filled in. There we go. So we got a disjoint segment this time. All right, that's pretty much it for, great question. Hold on. All right, now there's two more scenarios. So let's take a look at x is less than negative 4. So how do we solve this problem? Well, what does absolute value mean? It means make it positive. So is there going to be any value that we can put in for x that will be smaller than a negative number? No, because whatever's put in here becomes positive. So it's impossible for a positive number to be less than a negative number. All right, so 9 is not less than 6, so it can't be a true statement. And let's also think about absolute value of x is greater than -4. Well, what value of x will make this statement true? All values of x. If we put in -10 becomes +10. 10 is greater than -4. If we put in 13, 13 is greater than -4. So these are two special cases. When we're less than a negative, we know that there's no solution because no positive number is less than a negative. When it's greater than a negative, all solutions are possible because any positive number is greater than a negative number. So those are the special cases. All right, this was the examples and the lesson. Your next video will be the 4.8. Bye.